Hi, everyone. So today we're actually going to look at some of the angle formulas for sine, cosine, and tangent. To see exactly where these formulas came from, you can check for the link in the description for a proof of these sine and cosine formulas. And I leave the tangent formula as an exercise to you. You can obtain it by really just taking the ratio of the sine formula with the cosine formula and doing some simplifications. So for now, we're going to see exactly how to apply them more than where they come from. The most common application that you're going to see is really evaluating and in simplifying some equation solving using identities. So here, if I want to evaluate or find what sine of 15 degrees is, one option is I could go to a calculator, but if I want the exact value, I can actually use one of these sum and difference identities to help me with that. Because 15 degrees, if I'm trying to find sine of 15 degrees, that's really the same thing as sine, and 15 degrees I can obtain by combining two angles I already know. It's really the difference of 45 degrees with 30 degrees. So if I can rewrite 15 as this difference, I could then use the difference identity for sine to rewrite this expression as the sine of the first angle, 45 degrees, times the cosine of the second angle, 30 degrees, minus, notice the signs agree. If I'm taking a difference, it's a difference for the sine function. Cosine of the first angle, which is 45 degrees, times sine of the second angle, which is 30 degrees. So then I'm going to fill in each of these values. Sine of 45 I know is the square root of 2 over 2. It's one of those special angles I have memorized. Cosine is the square root of 3 over 2. Cosine of 30 degrees. Cosine of 45 is also root 2 over 2. And sine of 30 is 1/2. So for each of these, I'm going to get a common denominator over 4. So I can rewrite this as a single expression over 4, 2 times 2. And then the product of the first two, rad 2 with rad 3, will give me rad 6. And then I'll be subtracting rad 2 times 1, which is just rad 2. There I have the exact value for sine of 15 degrees. We can do this in radians as well. What's the exact value of cosine of 7 pi over 12? I actually prefer the radian versions because I can see this is over 12, and I can think of two of my common angles that when combined would give me a common denominator of 12. In this case, that would be some value of pi over 3. So I'm going to say n pi over 3, where I don't know what that numerator is. When combined with some other value, pi over 4, I want an n and an m that's going to give me 7 pi over 12 so that I can use one of those angle sum and difference formulas. This could just as well be a difference. If I wind up with a negative m, then I'll have a difference and I'll use the difference formula. That's why I'm just assuming it's a sum, allowing for that to be negative. So when I combine these, I get 4n pi plus 3m pi all over 12 should give me 7 pi over 12. Now there's lots of correct combinations, but just eyeballing, I noticed that if n is 1 and m is 1, so in the situation where both n and m is 1 in this particular circumstance, I get 4 plus 3, which is 7. So that's a circumstance that I can decompose 7 pi over 12 into really just 1 pi over 3 and 1 pi over 4. And that's how I can creatively break down 7 pi over 12 into a sum or difference so that I can use one of these identities. So if n is 1, then this would be pi over 3. And if m is 1, this would be pi over 4. So what happens when I sum these two together is I will get 7 pi over 12. And the reason I wanted to do that is so that, and I'm just going to take this out as a reference. If I look at these identities, and I'm just going to bring it down here just so I can focus on the identity I'm looking for, the sum identity for cosine is here. I can use that sum identity. It's just going to be in terms of radians this time. And I can rewrite this as cosine of the first angle, pi over 3, times cosine of the second angle, pi over 4, minus, notice that for cosine, the signs between these two functions are opposite, sine of the first angle, pi over 3, and sine of the second angle, pi over 4. Okay, these again are all special angles, so I do know those. They come from the unit circle. So pi over 3, if it helps to think of it in degrees, that'd be 60 degrees. Cosine of 60 is 1/2. Cosine of pi over 4 is root 2 over 2. Sine of pi over 3 is root 3 over 2. And sine of pi over 4 is root 2 over 2. So when I multiply these together, I get something similar to what happened in my last expression. I will wind up with the square root of 2 minus the square root of 6 all over 4. So it looks remarkably similar. And you'll see that patterning is very similar for sine and cosine for these angle sum formula applications. Another way that we could apply these angle formulas is in some problem solving. So here I have a problem where I know kind of like unit circle trig applications. I know the value for sine of the two angles, and I want to know what is cosine of their difference. Okay, so since I have the values individually, I see that I'm taking a difference, I'm probably going to want to apply the difference identity for cosine. So I'm just going to drag this down here. I'm going to highlight that particular identity. So I want the difference for cosine. So I'm going to start there, and I'm going to see how I can figure out how to apply these values as I go through it. So I'll start with cosine of a minus b, and if I apply this identity, this should be the same thing as cosine of a cosine of b plus, let me clean that up, went a little bit too quick, sine of a sine of b. Okay, now some of these I already know the sine values, so I can plug those in immediately. I know sine of a is 1/2, and I know sine of b is 4/5. But I don't know the cosine values yet. However, I do have enough information in this problem to figure it out. And it's really from these two values and the fact that I know that both are in quadrant 2. So what I'm going to do to figure out these angles is I'm going to sketch each one. I'm going to sketch A, angle A, and I don't know where exactly it is, but I know it ends somewhere in quadrant 2. And I know the sine of that angle is 1/2. So what I'm going to do is drop an altitude from a coordinate on the terminal side of this angle. And I know that sine is the ratio of the opposites of the hypotenuse. So that's going to give me the 1/2. And then I can kind of infer, well, this has got to be a 30, 60, 90 triangle to have a ratio of a leg to a hypotenuse of 2, which means it has to be 1, 2 to rad 3 ratio. And because I'm in the second quadrant, that x direction is going to be negative. So that should be a negative root 3. And then I can infer the cosine value, which is the adjacent over the hypotenuse. So cosine of A has got to be rad 3 over 2, quantity negative. You could also have inferred that if you see that sine's 1/2 and you know that cosine is rad 3 over 2, and in the second quadrant, cosine is negative. So that's a shortcut way, but I like to draw it out. I like to have a good conceptual understanding of what's going on. For B, we can do the same thing. I'm going to sketch angle B. Angle B, we are told, is also in the second quadrant. So I'll draw a terminal side. I'll find a coordinate and drop an altitude. And I will use sine's values, again, opposite over hypotenuse. So that's 4 over 5. And I recognize this as a 3, 4, 5 Pythagorean triple. Again, in the x direction, we are moving negatively, so that would be a negative 3. So when I infer that cosine value, it's the adjacent over the hypotenuse. I get negative 3 over 5. Okay, so now I have all the numbers. Now I just got to do some arithmetic and combine them. The two negatives will become a positive, and I'll get 3 root 3 over 10. I notice that in my second quantity, I also have 2 times 5, which will also give me over 10. So these will already have a common denominator. So I'll write them as a single fraction, and the numerators here would be 1 times 4. So I wind up with 3 root 3 plus 4 over 10 as my exact value of cosine of the difference of those two angles. Okay. One other form of application that we could have with this is in verifying trig identities. We've done that a bunch so far this year. So I want to verify the identity that the combination of these two yields this. Remember that when verifying identity, it's really a proof. So I'm just trying to show that deductively this left-hand side reduces to this right-hand side. Again, I'm going to bring my identities down here just as a reference. Now, since I see cosine with a sum and a difference, obviously I'm going to be focusing on the sum and difference identities here for the cosine function. Been using those a lot so far. And I'm just going to go through it. So I'm going to apply that identity and see what happens. So if here I have x and y in place of a and b, so I wind up with cosine of x cosine y minus sine x sine y for the value of cosine of x plus y. And if I do the same substitution for cosine x minus cosine y, I will wind up with plus cosine x cosine y, it's a y, plus sine x sine y, which is convenient because then these two values will cancel out, and my sum simplifies to 2 cosine x cosine y, which is exactly what I was trying to show it reduced to. So we can use these new formulas in a lot of different ways. They can be used like any other identity in terms of helping us to evaluate an expression, to verify other identities, or even in equations if I have an equation that I can't solve without some form of substitution. So we'll be exploring these more together.